And yeah, I'm very happy to start with a bang. We have a double feature today, starting with Amir Abboud, who will tell us about some exciting work, and then we will have after a minute break. We will decide. Okay, all right, thank you.
Okay, hello everyone. Thanks for walking in the cold to come to my talk. I appreciate it. So I wanna talk about this very simple question. I have two problems we really like. What is the relationship between them? What's easier or harder? So two problems are shortest path and connectivity. So connectivity, I mean like minimum cut or maximum flow. It's the same thing for me, and I'll use min cut or max flow interchangeably throughout the talk. So these are very, very basic graph parameters. You know, you have a graph, and these two parameters or problems or functions, they ask two different things. So in both cases, you have a graph and you have a source on a target, S and T. In shortest path, you're trying to go from S to T while walking on the cheapest path. You know, you want to choose a path that's made up of the cheapest total sum of edges. So in this example, it's like 60. And there's one problem. The other problem is the minimum cut or the max flow. So the max flow is you're trying to push the maximum amount of flow from S to T while respecting the edge capacities. But it's equivalent to the min cut, which may be easier to think about, where all you have to do is you have to separate S from T by deleting the minimum total number of edges. And this is the same graph, the max flow is 11. Okay, so these are two very basic problems. You see them in a basic algorithms course, and you may wonder which of the two is harder to compute. And I'll be talking in the standard model of computation. Weights are integers and so on. So for shortest path, we have Dijkstra's algorithm. It's very classical. It's a very simple algorithm, and it solves it very fast. If m is the number of edges, n is the number of nodes. It's essentially linear time. And so good. That's kind of easy and simple. For max flow or min cut, things are more complicated, and it took much longer for us to get to such good algorithms. So even just getting some polynomial time algorithm took many more years. And so it was with Dinitz, and there were some more improvements to that algorithm. And then in the last 2 decades or so, there was this method from continuous optimization with Laplacian solvers and things like that got the complexity down.
This for approximate, like
even for exact, so you can use them also to get exact. And even so, when I started my PhD, started thinking about these problems. These people I would meet them at conferences, and they would tell me, "Oh, it's going to be linear time. It's just a matter of analyzing it the right way and so on." So these techniques were clearly powerful enough to get us all the way to linear time, and this actually happened in remarkable breakthroughs recently. And so this result gives almost linear time. So if we ignore, throughout the talk, I'm going to be mostly ignoring these subpolynomial factors. I'm only going to care about the polynomials. And also, I'm just going to drop m and just analyze things in terms of n. So both of these things are like n squared. M could be up to n squared. So both of these things are like easy problems, like essentially linear time solvable problems. But of course, this is much, much simpler, right? This Dijkstra is very, very simple, very easy. This is, a very complicated paper building on a lot of hundreds of pages of work. Okay. But to summarize what I said so far, if you look at these two problems and you're in this, what we can call the single pair setting, where you want to know the answer for a single pair S and T, they're both at the same complexity. But if you think about maybe more general problems, you can start seeing differences. So you can notice that when you run Dijkstra, you don't only get the distance from S to T, you run it from S and you get the distance to all the nodes. You get this shortest path tree. So at the same time, you also solve the single source problem, where you have S and you want to know the distance to all other T's in the graph. And this is the difference between the two problems, because these algorithms, these very complicated algorithms, they don't give you that. If you wanted to know the single source information, you would have had to run them once for every target. So you can run them by choosing, ST1, T2 up to Tn, and you get this information, but it's going to cost you an additional n factor. And so let's look at the kind of most general problem in the setting, the all pairs problem, which will be the main focus of our investigation. So in these all pairs problems, you get one graph, you don't get S and T, and you need to output for every pair what is the distance, or for every pair what is the minimum cut or maximum flow. So you just have to output the values. You don't have to output the path itself or the flow itself. That would be expensive. Just output the value of the flow or the path. So the output size is these n squared numbers. That's the output I want you to give. What is the complexity of these problems? And so for shortest paths, we can just run Dijkstra from every source, and we get this n times Dijkstra complexity, which is n cubed. And again, this is a very simple, kind of very, very classical algorithm. For all pairs max flow, you can still do the naive thing of for every ST, run the single pair algorithm, and now you have n squared additional overhead, and that's n to the 4. But then in 1961, there's a remarkable paper by Gomory and Hu, which solved this all pair problem for min cut or max flow in a better time, in a time that's n factor times the single pair as opposed to n squared, which if you plug in what we know now for the single pair, you get n cubed as well. So let me spend one slide telling you about this Gomory-Hu result, because it's a kind of shows that this all pairs max flow problem is like fundamental beyond just being like a basic problem we like to think about. So what Gomory and Hu showed is this fundamental fact about graphs that says that you can take any graph, any undirected graph, even weighted, and you can turn it into what's called a cut equivalent tree. So what that means is there is a tree T on the same set of vertices, but it's a tree, so it's a much simpler graph. It has weights that could be different from the original weights, and it has a very strong property. It's a cut equivalent tree. So what that means is for any pair of nodes, S and T, if you want to know the cut in the graph, you can look at this same pair in the tree, compute the minimum cut in the tree. The same cut that you got, if you look at it in the graph, it would correspond to a minimum cut between them. So it's like an exact reduction. There's no loss. It's like a graph sparsification, simplification result, maybe the first in kind of the literature, which now has become like a whole industry of things. But this is like exact. There's no loss, and it works for every pair at the same time.
What's the time to construct?
Right. And importantly for us, they also gave an algorithm. Like the proof of existence was algorithmic. And it showed that you can compute it by making a call to a ST minimum cut algorithm n-1 times. And I'll show this algorithm later in the talk. But yeah, so if you had the tree, then the all pairs max flow problem would be easy. I mean, all you have to do is solve it in a tree. Minimum cut in a tree, you just need to find the cheapest edge on a path. You can then solve it in n squared time. Like it's some easy exercise. But the main thing for us is, how do we get the tree? How fast can we compute the tree? They gave this algorithm that's n times max flow. And since their work, it has been open question to get anything better. So can you reduce the number of queries below n? And there was no progress on this since then. Meanwhile, if you go back to the shortest path setting, where we had this n cubed algorithm, and also people have tried to improve it a lot, and there was some progress. So there were log factor shaving results, and even there was a result by Ryan shaving a super poly log factor. And so it's still at n cubed, like the polynomial, but it looked like there was something happening here. Maybe this was going to break or something, but nothing was happening for max flow. So the bottom line is that they're both at n cubed, but shortest path seems easier. And this is basically what all I've said so far. So we have these two problems, max flow, shortest path, all pairs, they're both at n cubed. And our feeling was that max flow should, if one of them, okay, the question was which one is harder. Our feeling was that max flow is harder. And let me give you two more reasons to think that way, which we thought. So one reason is if you look at unweighted graphs, so you just remove the weights, all weights are 1, what happens? For shortest path, you can use fast matrix multiplication and you break the n cubed result. So there's this classical n to the omega algorithm. Whereas for max flow, we didn't know anything. You couldn't beat the Gomory and Hu result. So that's one reason. So for this kind of fundamental setting, there's a kind of separation. And if you look at directed graphs, another interesting setting, for shortest path, everything still works, direct still works, so you still get n cubed. But for max flow, this Gomory and Hu result fails. So directed cuts are just much more complicated than undirected. You can prove that there isn't such a thing as a Gomory and Hu tree. So the best we know is n to the 4, which is much higher than the shortest path. So like these two kind of settings, we do have separations. So yeah, these are just some reasons to think that max flow is harder. So that's where we're at. We feel like max flow is harder. Can we prove it? And this is where fine grained complexity comes in, which is this kind of literature where we take problems, fundamental problems, and we try to find connections between them. And whereas kind of before we had all these nice problems, polynomial time solvable problems, we didn't know which was harder, which was easier. But we developed a lot of reductions that let us draw a nicer picture that gives us some kind of understanding where there's some core problems that maybe a lot of people have thought about, and there's famous conjecture saying that for those problems we have reached the right bounds, and then you can reduce these core problems to dozens of other problems and explain their bounds, and showing that for all these other problems you cannot solve them faster unless you break these famous conjectures. And importantly for us, all pair shortest path is one of these core problems for which there is a conjecture. So the conjecture says that you cannot beat the cubic bound for APSP. And under this conjecture, there are reductions and conditional lower bounds for a lot of basic graph problems, even very, very simple ones. But notably, all pairs max flow is not in this list. And it was very natural for us to try to put it in the list.
Yeah, it's notable that this conjecture is equivalent to the version for directed graphs too, which also seems to indicate that like this is different from all pairs max flow.
Right. For
They're literally equivalent.
To the directed.
you can
Directed
reduce
and
the
undirected
directed
cases are actually equivalent. Not only does directed work,
APSP,
but
yeah.
they're literally equivalent to APSP.
Yeah.
But probably not for all pairs max flow.
So we had this class, all pair max flow was not classified. We really tried hard to do it. It was something I thought about from a very long time ago. And we did have some results. So we did show what we believe, that max flow is harder than shortest path, but we could only show it for directed graphs, which is, as I said, is not a very interesting setting because directed cuts are weird. And the Gomory and Hu result doesn't really apply. So we basically showed that this bound probably cannot be much faster. This is different depending on the conjecture, and I don't want to go into the details. But for example, there's an n cubed lower bound under Ceph. Good. So we confirmed what we believed, but not for the like the fundamental question we were asking about. So let's forget about directed graphs and let's go back to the undirected graphs and see what we know there. And we didn't know anything, so we didn't have any lower bounds. And here I want to give like conceptual credit to fine grained complexity So when I started looking at these things, this is a list of problems that I thought are very nice problems, very fundamental problems that we should really solve and so on. But it was a mess, and I wouldn't, all-pairs max flow was one of them, but I wouldn't spend years and years working on it because, there's all these other problems I could be working on, and why spend all my time on this one? Maybe I'll fail and so on. But then after I finished my PhD, the picture was very different. So for my list, so there was these red problems. These are conjectured to be hard problems. You have to be very, very brave to work on them. So on. And all the other problems were grayed out. So we knew that you cannot solve them faster until you solve a red problem faster. So working on the gray problem is also something that you have to be very, very brave for. But then all-pairs max flow really stood out as a problem where we didn't know. And I did think it was really worth studying at that point. And at that time, Ohad Trabelsi was a PhD student of Robe programmer, came to do an internship at IBM with me. I said, let's work on this problem. And we've discovered a bunch of results. I don't want to go into the details, but making some kind of progress here and there, explaining why we don't have reductions and so on. Until we discovered this result, and we were very, very happy. We got the first improvement over Gomory and Hu. It was only for unweighted graphs, but we broke the cubic bound. So we got into 2.5 time. And then things started accelerating from then on. 6 months later, there were 3 papers on arXiv improving this all the way to n squared. So what happened is that this thing dropped from n cubed to n squared, which is great. It's like a tight algorithm. N squared is like the output side. I mean, optimal is great. And for the first time kind of in history, this max flow became easier than shortest path. And yeah, so what's going on? We were very, very confused. But then maybe the answer to the confusion was that, well, just like the experts were telling us that max flow will be linear time, the experts are also saying omega will be magic multiplication will be linear time. And so maybe this is just n squared and there's no separation. Both are easy problems. And that's what it is. So then, okay, if that's true, then the real question is for weighted graphs, where if you can break this bound, then you would get this counterintuitive separation, because here, the experts are putting this conjecture, as opposed to this, we don't really know we don't really believe, or we don't have strong reasons to believe that this will be broken. So then if you do break this, then you would separate that into 2 problems. And yeah, so about a year or 2 later, this actually happened. So we solved the general weighted case also in quadratic form. This is with Jason Lee, Dimalia Panigrahi, and Tachafol Saramura.
So it's again finding the Gomory with 3 in.
Yes, so the algorithm not only solves the problem, but even finds the Gomory-Hu tree of the graph. So good. So under the APSP conjecture, if this is the right thing, then we got the opposite separation of what we were setting out to prove. That max flow is actually a much easier problem. And so maybe the conclusion is that maybe this conjecture should be broken. And either you accept this or you try to break the conjecture. And this, I'm gonna spend the last part of the talk on this. But yeah, before I talk about this, how you might inspirations from this work to try to break the APSP conjecture. I want to spend a bit more on the max flow result. So, and just before we get to the technical part, some follow-up works. So, for computing the Gomory-Hu tree, n squared is not satisfying. You may want to compute it in linear time, and we actually did that too. So, you can take a graph, has m edges, could be sparse graph, in linear time, produce the tree, almost linear time. And then once you have the tree, you can just look up the all pairs information. So you don't. And the title of the paper is that the all pairs max flow is not harder than single pair. So it's like a reduction from all pairs to single pair that has just polylogarithmic over. That was the first thing we asked. The second thing we asked was the randomization was randomized, and this is more recently we got everything to be deterministic as well. And then the third question, so these are three questions we asked in that paper. The last question was whether we can simplify things. So I didn't show you the technical, but it was pretty complicated, using a lot of different things and so on. These guys, Rasmus King, Max Gutenberg, and Yuan, they have been working, and this is very recent, like last week at Soda and Sosa, they have been simplifying, and a lot of the fancy things that we've used are now not necessary, which makes my life easier for the technical part, because then I'm not feeling guilty about not telling you about all this fancy stuff. So I'll just focus on the thing that will actually, as they're showing, is kind of all you need. So good. All right, so the next part is going to be some kind of technical overview. It'll be a pretty high level, trying to inspire you to think, to get something from the APMF results, but then inspire you to think about the APSP, the goal. Okay, so I want to, draw like a high level picture of what these algorithms is, which you can say it's a general thing about modern algorithms and how they work. So there's like three main components, some combinatorial algorithmics, some structural analysis, and some heavy tool. And I'm gonna say what these things are in the context of max flow, and then we'll try to say what they might be for the context of shortest path. So the heavy kind of the tool, the kind of the powerful tool at the end that you use for us for computing all pairs max flow is the single pair algorithm. So this is something we use like as a black box. At the end, what we're doing is a reduction to single pair. And this is, it's a tool that to actually solve it in linear time, you need to use this optimization and lesson system solver, dynamic data structures, and so on. Okay, but like our work is kind of on top of it, like on the other things, leading us to this reduction. And so the first thing that is always there is some kind of combinatorial algorithms, which we're using things like, divide and conquer or sampling and sorts of combinatorial.
It's going to be a linear time reduction, near linear time reduction.
Yes, at the end of the day.
For many pairs to single pair.
Yeah. The overhead is polylogarithmic overhead. In fact, it's not like we're only going to make polylogarithmic calls. No, we're still going to make n calls, but they will be on smaller instances.
In the
Fine grained.
divide and conquer,
grained.
yeah.
Yeah.
The total time of the thing will be just linear. Right. Okay, so there's this algorithmic stuff. And then one thing that's kind of there in we might say in modern algorithms is some kind of data-dependent thing or some kind of structural analysis of the input itself, where you do something for the input, for the graph, something like an expander decomposition or something else that we've used here, like standard tree packing. And it lets you really kind of, it just helps the algorithmics basically, and I'll touch on how that happens. But you can think of this as also as a worst case to average case reduction for your problems. It's like, you do these things and you wish the graph was random. If it was random, you're happy. So then you try to find some way to make it random. Okay. And okay, so these things, this is like new for the Gomory Hu. I'm going to start with the Gomory Hu algorithm. It was just like basically this and this. So I'm going to start with that now. Okay, and what I want to show you is actually a reduction from Gomory Hu construction to the single source problem. So like reducing all pairs to single source. This is one of the new things we have done, which so it's one of the ideas I want to share with you today. So, and then the way I'm going to explain it is I'm going to start with Gomory and Hu and say how a single source might help you. Okay, so let's go back to 61. This is what the Gomory and Hu algorithm does. You have your graph, you want to compute a tree, the Gomory and Hu tree. So you start with, you put all the nodes in one super node, and you pick an arbitrary pair of nodes, S and T. You ask for the minimum cut between them, the ST minimum cut. So you get the cut. And so you use this cut to divide your supernode. Okay, so you know, one side of the cut goes here, the other side goes here, and you put an edge between them with weight that corresponds to the weight of the cut that you find. Okay, and you continue. It's like a divide and conquer thing. You divided it, and then you want to continue recursively on the two sides. But a critical thing is when you continue, so let's say you want to continue on S, you have to contract T. It's like a clever thing that happens. So you take T, you contract it into a single node, you adjust like the edge weights, and then you do the same thing on the contracted graph. You pick a new pair, arbitrary pair, you find the minimum cut between them in the contracted graph. So let's say maybe this is the new cut, and you use it to make progress on S, to separate S. The contraction is very important so that the cut that you find doesn't mess up the other side. So then you really end up with a clean tree structure.
The partition may not be balanced. It may be.
The partition may not be balanced. Yes, we wish it was balanced. I'll get to it in the next slide. But the fact that this is correct, that this contraction doesn't cause you to get suboptimal cuts, this is what's called the submodularity of cuts. It's a lemma from Gomory and Hu. It's very important. So that's it. That's the Gomory and Hu algorithm.
This works for any submodular function.
Yeah.
On that,
Yeah.
You always have a tree which captures the.
Mm-hmm. Yeah.
Can you say something about it?
But what?
Like, why is it true?
Oh, why is it true? No, it's just calculations basically. If you work on it, you can just move this or this would be better, kind of. It's
Okay.
just a proof by calculation. Okay, so that's the algorithm. How much does it cost? What's the time complexity? So notice that we're gonna keep doing this and discovering new edges. Every time we make a call, we discover a new edge. So we're gonna have n-1 calls. At the end, the tree has n-1 edges. The number of calls that we're making is n-1 always. But you might hope that these graphs are getting smaller and smaller, and that you're contracting. So then you might hope that the total size is good. And unfortunately, let me say, if the cuts were balanced and you were cutting in half and you're contracting, and you have this, you'd have like a log n depth tree, and every layer you'd have the linear size total. You'd be very happy, and that's kind of where we would like to go. The issue is that this doesn't always happen.
If your input graph is an expander, can you show that the graph indeed gets smaller?
Great, so thank you for the question. Actually, expanders are actually the worst case here. So let me say, so what is the worst case? The worst case is whenever you pick a pair, the cut that you get is T is on one side and everything else is on the other side. So you only reduce the graph by one, graph size by one. And then you pick another pair here, and again, you just remove one. So the depth would be n. And I claim that this Gomory and Hu, this is the final Gomory and Hu tree. I claim that this is what you get in an expander. And to see this, imagine you have your graph as an expander. This means that if you have a pair of vertices, the minimum cut between them is just take your degree. You take your, the minimum cut would just be equal to the degree. And this is what you would expect in an expander, because if you go kind of further away from you, like somewhere in the middle, it's an expander, so there will be a lot of edges crossing. So this kind of thing is not a contrived example. It's actually what happens a lot.
But it could be a path other than itself.
the Gomory.
You remove a vertex and you remove another one. It's not clear it will look like.
A path where the edges are increasing. You don't want to. You're saying a graph where the minimum cuts are actually the degree cuts could be a path.
No, I see you.
Yeah.
Okay, it doesn't find it right. I mean, because as you said, the expander is degenerate in the sense that the minimum cut is always the same.
Just the degree, yeah.
Yeah.
Yeah. So you don't make enough progress, basically. And as you can observe in expander, for example, even if you pick these pairs at random and so on, it doesn't help you. You're still going to get the degree cuts. So one idea that underlies a lot of what's going on is that it's like you want to compute not just for a pair, you want to compute a lot of minimum cuts at the same time. And one clean way to do it is with single source cuts. So you pick a pivot node and you want to compute the minimum cut between them and everybody else. And we don't know how to compute this in linear time, but suppose we could, then everything will just work. You pick the pivot at random, you find these minimum cuts, and you can show that with high probability, all of these cuts, it'll let you kind of recurse into a constant fraction of instance sizes.
Wait, why is this true for expanders?
So for expanders, if you pick a node, then the minimum cut, the single source minimum cut from that node to everybody. It's true that you might worry that it's that node versus everybody else. That's the best cut for everybody else. But it might also be that they are on their own, and so it's like you can pick the latest cuts if there's a tie. But if there was no ties, then for half of the vertices, it's not I'm on my own. It's not the pivot on its own and everybody else together. It's that they are on their own. And
I see. So you get one big component and the other isolated nodes.
exactly, you get half on one component and then half are isolated, and that's progress.
So previously, your reduction was using a single pair cut, right? And that is every time you will expand one node into an edge. So how do you get this structure? Like, how do you go from one node to 3 parts?
If you had these cuts, then you would need to adjust the Gomory and Hu strategy. Instead of learning one edge at a time, you're learning a few edges at a time. So you recurse here, you contract everything else. And so it's kind of you adapt the Gomory and Hu algorithm that way. But if you're asking about computationally, this is a big difference. We don't know how to compute this efficiently. For single pair, we knew how to compute it. This, you have to work hard to compute the single source cuts.
Can you say about the reduction? Like if you have these single source cuts, how do you go from like one node to the outcome of your single source cut? Like what are the 3 parts?
We would like this to be the output of the algorithm. So I see, I didn't define the single source min cut problem properly, but so for the purpose of the talk, just assume you get these. You're saying that, for each of these nodes, there could be like a smaller cut
No, I
we
mean,
need to.
what are the 3 parts?
The 3 parts is, think of it that for these nodes, for everybody here, this is it's not quite. It could be that for this node there's a smaller cut. So there's like a nesting structure of the cuts. So this cut is the minimum cut for somebody here, but then for others there could be even better cuts.
So is P a node or a supernode?
It's a node.
It's a random node.
It's a random node. Yeah.
Okay.
Yeah, it's I didn't want to go into these technicalities of how it's defined. You're right that it's a bit subtle. Okay, so that was like kind of this part, this sampling and so on, divide and conquer. Now I want to explain how this goes into the picture. It's data-dependent stuff.
Yeah, but you still don't know how to compute the single source
so-
counts in linear time, so this will solve this problem.
Yeah, so the main thing now is how do you compute the single source min cut? And this is where we're actually going to need some data-dependent things, some kind of... Specifically, I'm going to explain how expander decomposition goes into it and helps you. So this is why it helps you. So imagine you want to solve the single source problem. You have your source. And so you compute an expander decomposition of your graph. An expander decomposition is a decomposition of the graph into such that every component is an expander, and there are few edges are left outside. And the few and how much of an expander and so on, there's a trade-off here. You can choose it. I'm not going to go into it, but just as a picture, this is what you have. And then you want to know the cut from P2 to all the other nodes. And as a wishful thinking, you might hope that these minimum cuts, they will never cut expanders. So they will always go like this. So an expander will always be on one side of the cut. And so if that were the case, then, it's easy because then you can treat kind of a contract expander. You can, for every expander, you can only do one query. That would be good. And of course, things are more complicated, and it's actually possible that you will cut a small piece of expanders, and this creates a lot of complications, and we had to deal with this. But this is more like algorithmics.
But also the number of expanders in the composition method.
Yeah. I'm rushing so much here. There's to choose the parameters. You might have to do this because it's a lot of work. And these guys at the SOSA paper, they're trying to make it cleaner and cleaner. It's still not enough for me to present everything in an hour or two. But I just wanted to share this as a main idea of what's going on. And I'll just quickly flash this. I'm going to skip it so I'm running out of time. One of the main new algorithmic things. Okay. Okay, so then I'll share this slide or two. So this is one of these algorithmics that was really important and needed to help you with the case of cleaning up these kind of pieces and stuff. But it turned out to be so useful that now there's like more than 20, 30 papers on cut algorithms in the literature that uses this result. They generalize it now to everything. Hypergraphs, all these different models. It's a very simple thing that actually very easy to prove from the Gomory and Hu result, but somehow it has been very helpful. And so let me just say what it is. It's a result. It's a new problem. So the problem now is you get a graph and these terminals, say K terminals, and you want to compute the minimum isolating cuts. So these are the minimum cuts under the restriction that there's one terminal on one side of the cut. So you're trying to separate one terminal from all the other terminals. This is the cut that you would find. Okay, so it's a kind of like a multi-way cut problem. The cool thing about it is that you can actually compute it. It's not an AP hardcopy. It's an efficiently computable. You could have computed it in K times max flow by just doing it one for every terminal. You contract all the other terminals and you compute the minimum cut. That's what you're looking for. But it turns out you can do it with just log K instead of K.
So there is just a node, right?
It's just a node. There's a subset of the nodes that you care about, basically. Yeah. So the super useful thing is that you can do it with log K instead of K. And it's some simple thing where you take half each time and you do it. And let me just say quickly, like at a high level, why this is useful. Like imagine you sample, you're worried about a cut that's like not balanced. So your graph might have a lot of small cuts that you want to compute all at once. If you sample terminals at random and your cut is small, then you're likely to hit only one of them and not more. So then you compute this once and you kind of find all the small cuts at the same time. Then you only have to worry about the big cuts, and then the expanders somehow are better to handle those.
So for example, in the expander example, you have this situation where every cut is very small.
Yeah, but expander is so easy that, yeah, but for expanders, yes, like, but expanders is like, okay, you have like the guess that the degree cuts are like your first guess, and they're correct for expanders. But sometimes you have these graphs where every three need to be together. And then, like, how do you efficiently find your friends? Like,
Okay, and who would be the terminals in that case?
just pick everyone at random with probability like 1/3.
Okay.
So one of the three will be chosen, and you will find all the triples in one call. Okay, so the high level of our algorithm is like this. So you want to compute the Gomory Hu tree. You do this reduction to single source min cuts. Then you do the structure analysis. And for the unweighted case, we just use expander decompositions. It's pretty simple. And then it helps us get to this polylog calls to this isolating cuts thing, which then reduces to polylog max flow. For the weighted, we couldn't break the cubic barrier at all. With just expanders, we had to introduce a new kind of graph thing, which is based on Steiner tree packing. It's very fancy, very nice. It generalizes Karger's work on tree packings. Those Sosa papers are showing that this is not really necessary. They can do everything with expanders, so I'm not feeling guilty about not telling you about all that stuff. You still need it to get all the way to linear time currently. Okay, so that's the end of the max flow overview.
So can you go to the right side? So the isolating cuts, the algorithm is going to help the cuts through the expanders or across expanders.
It's gonna help you with the cut few of an expander that really touch expanders. Those you will also do isolating cuts and so on. Like you will pick the terminals from the expander, for example. I didn't explain it, but it's
Okay.
it goes into that. Okay, so good. So for the last part of the talk, I want to talk about APSP. And so this is inspiring us to doubt this conjecture. And yeah, so let's see how can we, what can we do? And first of all, I want to start by saying, okay, like this fine-grained complexity, these conjectures, they're great. We're building this thing, but they're not meant to be as untouchable. I view this work as saying, there's these hundreds of problems. Don't work on these hundreds of problems until you break the conjectures. And once you kind of classify everything, now we should really be working on these conjectures, trying to break them. It's like saying, before we didn't know what to work on. Now we know what to work on. We have these three conjectures. Now is the time to really attack them. If they break, it'll be a mess. But that's kind of like now it's kind of we're more focused now. So, and I just want to quickly say like what would happen if this conjecture breaks APSP. So in fact, APSP there's like even stronger versions of it that are out there that people have used as conjectures, and you can think of them as saying that APSP is still true. You cannot solve it even if the graph has certain structure. The graph is a product graph, or if it comes from some kind of convolution, or if the weights are small, or if you just want to compute the largest weight, or things, restrictions on the problem. So when I say let's attack APSP, I'm also saying let's attack these harder versions and say which ones are actually false. But yeah, but then APSP has its equivalence class. So there's a bunch of fundamental problems that are equivalent. So if you solve APSP faster, a lot of its class will just be solved with it. So you would solve a lot of problems as well. Of course, you would refute the other stronger versions, and they have some of them have their equivalences. But then for a lot of problems, this is just one-way reductions. So you would get this class of problems where the lower bounds fails, but we don't have faster algorithms. And then you just have to work on them. Okay, so how do I want to, describe some attacks on the APSP conjecture, share some recent progress under this kind of framework of some combinatorics, some structural analysis, and some heavy tool. And so, of course, in everything, we're looking for new things, but let me just suggest some of the things that are out there. So some of the work here has been done for us. Specifically for APSP, there's has been studied a lot and we know a lot. So some of the most, this is great work allowing us to focus on just the triangle or matrix problem. So let me explain what I mean. So what I kind of mean is that all you have to do is look at these graphs, these three-layer graphs. So let's start with the unweighted APSP thing, and then we're going to move to weighted. But this is actually how you solve the unweighted APSP. I said you can solve it with fast matrix multiplication and n to the omega. So this is how you do it. So you go from unweighted APSP to Boolean matrix multiplication, where you want to compute, this kind of product, which kind of as a graph thing, you get a three-layer graph, and you want to know for every pair on the left and on the right, is there a two-path? So this Boolean matrix multiplication is just this, where this is a matrix.
And it's a complicated reduction.
Sorry.
I mean, you start with shortest path on the general graph and you reduce it to this kind of graph. How complex is this reduction? They are equivalent, to say.
So they're equivalent in the not really. So it's not true that they're equivalent n to the omega. It's not quite true. What we know is if this is subcubic, then that is subcubic. It's at a high level, you can think of it as some kind of repeated squaring, going from this to dash longer. So you have long paths. This gives you the two halves, and okay, and then if you go to weighted APSP, so here we know the subcubic, here we want to get subcubic, we don't know. So you can still do the same thing, and what you get is this min plus matrix multiplication, where instead of the and, you get a plus, and instead of the or, you get a min. And again, what it really says is for every pair on the left and on the right, you want to find the cheapest two path.
Virginia and I came up with this equivalence while we were here.
Yeah, well, I remember that
Here,
exactly. I didn't remember anything about that.
I don't think we told you about it then.
Yeah.
Good, so we have this weighted thing, this min plus, and we want to solve it faster in subcubic time. And I think there's two ways to go about it. One way is to still reduce this min plus to the normal matrix multiplication, the plus times, which is how you solve the Boolean other thing. And here the idea is to somehow, remove the weight. So, you have the weight, you want to get rid of them or handle them better and so on. And for here, you can even assume omega is 2. And this is something, whenever I'm thinking about this direction, I assume omega is 2. It doesn't really matter. And you just want to deal with them better. But there's a different approach that says, let's try to solve the unweighted thing in a new way and hope that this generalizes. So the thing is, this regular matrix multiplication, it doesn't, the way you solve it, Strassen and all these improvements, they don't allow you to solve them in plus. There's very clear barriers for that. So you can either reduce this to that, or try to come up with something new for this, or rather for the Boolean, that would generalize to min plus. And this is kind of what this second direction is. And it's described under this search for a combinatorial algorithm for BMM. And the point is, you're just trying to find a new algorithm for the unweighted case and hope that it would generalize to min plus. So there's these two directions, and I think both are promising. In particular, if you think about the random case, then for both of them, it's easy. Like
What's random?
if the graph was random or if the weights are random, yeah. If you do these kinds of exercises, then oh yeah, it's easy.
Why is the right-hand side easy for random case?
If you have random weights here and there, it's been known for a long time that you can actually do it in quadratic time. You can so imagine if the weights are random from 1 to n, then you
I
expect.
thought you mean it's easy to reduce mean plus 2 plus.
Oh, sorry. No, I meant
The problem can be solved.
the problem.
That makes sense.
So I want to spend a bit on each of these directions and report some new progress on them. So good. So for this direction of coming up with a new algorithm for the unweighted case, so let me tell you what is known. So you want to solve Boolean matrix multiplication. What can you do other than use fast matrix multiplication? So there's this 4 Russians technique, classical one, which gives you a log squared shaving. There's these works that do divide and conquer and get some log cube log the 4. And there's another method using regularity decompositions by Ryan and Nickel Bansal, where they were able to get this 2.245, and recently we got a super polylog shaving with the same framework. So let me tell you a bit about that. But here, like the point I'm trying to make is maybe the regularity lemmas are like this structural analysis tool that we need. Again, because random is easy. And so how does regularity lemma come in? So you have this graph, you can do a regularity decomposition, decompose it to a small number of graphs, and each are regular. And then, once you have regular, it's like random and it's easy. But the bounds that you get from this really depend on the notion of regularity. Like, what does it really mean to be regular? And there's the Simonyi notion, there's the Friskanen. These give you different bounds on the number of graphs that you get, and they result in different bounds for the problem. Exactly. Yeah, so the one we use is grid regularity. It's very similar to what Kalimeka used for arithmetic progressions. And so we got this better thing because the number of, the thing is, like, here you're going to weaker and weaker notions. So this is a weaker notion. To be regular under this notion, you're not necessarily regular under these other notions, but you can show that it's enough to make the problem easy. And you gain. And so the question here now.
For the 3 AP problem, Berhan's construction gives you some lower bound of 2 n over 2
Perfect.
squared.
Yeah.
Does that imply any technical barriers?
Yeah, great. So that's exactly what I was going to say.
Oh.
So the question now is, can you do better? Maybe a different notion or something to go beyond to get a polynomial improvement. And as you pointed out, Berhan's construction is a well-known construction that of a graph that seems to be regular or is regular under a lot of notions, but it has this kind of dependence. So we don't know. We suspect that Berhan's construction is regular under this notion. We could improve it. So this one question, open question. Like, it seems to be a barrier. Is it really a barrier? I'm not sure technically.
I think it's not, but if you remember, I thought that was unlikely, but we didn't go to either way.
Yeah, so that's one question. The other question is, of course, you can come up with new notions. And one thing I wanted to say, so there's these stronger versions of APSP. The same happens with the Boolean matrix triangle detection. You can think of like the K-clique, which when you translate it to triangle or Boolean matrix, you get a graph that's a graph product of other graphs. And there, I'm pretty sure Berhan fails completely. So there is no barrier there to do it. I don't know how to. So what I'm saying, like this same notion could still work for these stronger versions. I don't know how to prove it, but hopefully that'll inspire you to think about this. Good. So that was the first direction. Now back to the second direction, where omega is 2. We want to use fast matrix multiplication, but we have the weights. How do we handle them? And like in this scheme of things, I have this heavy tool I want to use. But I still might apply something here. And just as an example, Ryan's current best algorithm for APSP can be viewed that way. So, he uses polynomial method, circuit complexity to get a reduction from n plus to plus times. If it was better, we could get better, but that's what we get. I'm going to talk about other things that don't go through this approach. And here I want to ask, okay, so what are these hard instances of APSP? Like, where are we stuck? And we didn't really know much about this. I mean, let me tell you some of the things we didn't know. So, okay, so we have these weights. So what are these weights? What do they look like? Random, we said looks kind of easy, but so the things we knew is this. So if you look at the maximum weight, you can get this bound, and the max weight times n to the omega. So if the max weight was sublinear, like smaller than linear, then it's subcubic if omega is 2. And it was conjectured, so this conjecture called the strong APSP conjecture, that the hardest cases are when m is n. So, so even at the threshold where, if the weights are smaller than n, we know how to solve it. If the weights are n, this conjecture said that this is as hard as APSP. And so it was open, and it was even open more basic things. Like it could be that the number of distinct weights is small, and that's still hard. So it could be that on all these edges is only root n weights. Is that hard or easy? We didn't know. So recently with Nick Fisher and Sejin, Virginia, and Xu, we answered this question. So we showed that, yes, it's easy when the number of distinct weights is small. So if the number of distinct weights is sublinear, then it's already small. And very recently in a paper I'm super excited about by Nick, he showed that, he answered this question. So he showed that APSP and strong APSP are equivalent. So he showed that you can take any weights and reduce them to n. And so this result really puts us at a very good place where we really know what the hard cases are. The weights are from this interval of 1 to n. That's all you have to do to solve it. And both of these results are using additive combinatorics, which is my last slide. So we use the BSG theorem, famous theorem from additive combinatorics. Nick needs, in addition, to use conjectures, something called PFR conjecture, the polynomial Freiman-Ruja conjecture. So his result is its equivalence is conditional on some additive combinatorics. Okay, so how does additive combinatorics go in? So I view this BSG theorem as just another way of getting regularity, some kind of structural analysis of the weights. And quickly,
Yeah,
the Velox already go.
yeah.
Yes. And so this is a theorem that says you have a set of numbers, set of imagined weights. You can decompose them or cover them with few sets, such that every set has a small subset, and that's a remainder. And to really show why this helps is, I just want to say that there is a generalization of this algorithm that depends on the max weight to this kind of bound, where if you look at the set of weights, and if the sum set of the set of weights is small, then you get something good. So it's kind of a similar algorithm. And so this really shows that if you could decompose the weights, or if you had these weights had small sum sets, then you would be happy. So then all you have to do is apply BSG and work with that.
Wasn't the polynomial Freiman-Ruja conjecture result though you're talking about?
Yeah, sorry.
BFR was solved.
So
Some version.
some version was solved over F2 or something. He needs it for integers or something.
Yeah.
The thing he uses, I think, seems to be very plausible, but not there. Okay, so that's the end of my talk. Thank you.